All right, so this is probably the difficult question in the set. It actually looks a lot like the gravitational force question we had a while back, where we have a constant multiplied by two special numbers, so charge 1 and charge 2 in this case, instead of mass 1 and mass 2, and then over the separation distance squared. So remember we did the question with the moon and the earth and the force between them. This time it's just the force between charged particles. So the good news about this is that most of these numbers, a lot of this information is all constant. All right, so K is a special constant. It is 8.99 times 10 to the 9. So this is right about 9 billion. This is a big number. The units are ugly, but it's a constant. It's made to cancel a bunch of stuff, so that'll be helpful later. We've got newtons times meters squared over coulomb squared. So kind of an unusual combination there. Then I'm going to leave some space right quick. So we have a charge coming from a bunch of protons. If we remember that each proton had 1.6 times 10 to the negative 19 coulombs, then we can multiply kind of like we did on question 1 to find the charge right here. Then we have another group of protons. And again, I'm going to leave space because we know that each of those is going to be 1.6 times 10 to the negative 19 coulombs. And then on the bottom, the separation distance is in nanometers. So nanometers is 10 to the negative 9. Again, I'm leaving a little blank here. But I want to show you, and the reason I've done all of this and left these blanks, everything that's in red right now is going to be exactly the same on this question all the time. The part that actually changes from these numbers in the question is the number of protons, the other number of protons, and then the specific number of nanometers. So we have 15 here, a 19 there, and a 22, and everything else is the same always. So keep that in mind when you're working on one of these questions later and you're trying to work it out for the test. A lot of this is very consistent and the same. So technically, if you wanted to, you could combine some of these constants and bring it together. It's a bit of a shortcut, or at least it's just less stuff to remember. The other good news is, oh, I dropped it. I forgot my meters down here. But our units cancel properly, right? We've got meters squared on top and then meters on the bottom that get squared. That's going to go away. Then coulomb squared here will cancel with each of these, and then all that's left is newtons, which is what we're looking for anyway. So all that's left is just sort of the chore of running through and finding the values here. So each part separately shouldn't be too bad. So like squaring on the bottom, 4.84 times 10 to the negative 16. We know this is newtons because that's all that was left over. A little bit more work, but multiplying all the stuff on the top is really just a bunch of calculator buttons. Shouldn't be hard, it's just tedious. That's going to give us 6.5591 times 10 to the negative 26. And then the tricky part is dividing these. On some calculators, you may need extra parentheses. You may need to be extra careful. But if you can make it work overall, you should get 1.355 times 10 to the negative 10. So even though these are really close, nanometers are tiny, we have an absolutely minuscule force. 10 to the negative 10 is less than 1 billionth of a newton. So very, very, very small.